Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to discuss applied thermodynamics lecture number 6, and lecture number 6 is about the properties of perfect gas. The objectives of this lecture are: first, we will discuss about the characteristic equation of state and its various forms, thermodynamic properties of perfect gases will be discussed comprehensively, and we will solve examples on these characteristic equation of state and thermodynamic properties related to perfect gases. So first of all, the ideal gas equation or characteristic equation of state for a perfect gas. Any equation that relates the pressure, temperature and specific volume of a substance is called an equation of state. This is very simple. Property relations that involve other properties of a substance at equilibrium states are also referred to as equation of state. There are several equations of state. Some are simple and some are very complex. The simplest and best known equation of state for substances in the gas phase is the ideal gas equation of state. This equation predicts the PVT, pressure, volume, temperature behavior of a gas quite accurately within some properly selected region. Gas and vapor are often used as synonymous words in this context. The vapor phase of a substance is customarily called a gas when it is above the critical temperature. Vapors usually imply a gas that is not far from a state of condensation. In this discussion, we can say that very superheated vapors can be considered as gas. In 1662, Robert Boyle, an Englishman, observed during his experiments with the vacuum chamber that the pressure of the gas is inversely proportional to their volume. So P is inversely proportional to the volume, and this is called Boyle's law. Similarly, in 1802, Charles and Jelousek, Frenchmen, experimentally determined that at low pressures the volume of gas is proportional to its temperature. So when we increase the temperature, the volume of the gas increases at low pressures. So combining these two laws, Boyle's law and Charles' law, we get this equation: P is equal to R into T by V. If we rearrange this, we get this form of equation: PV is equal to RT, where P is the pressure, V is the specific volume, and R is specific gas constant or particular gas constant, and T is the temperature. Other forms of the equation may be like, further, if we consider that specific volume is equal to volume per unit mass, so capital V will be equal to m small v. Or simply we can say that if we replace this volume, specific volume, by V by m, we will get this form of equation, that is P capital V is equal to mRT. Small v stands for specific volume and it has the unit cubic meter per kilogram. while sample V is the volume only, and it has units cubic meter. So after putting the specific volume V by M, we get this expression of ideal gas equation, that is P V is equal to mRT. Further, we can introduce other terms in this equation like molar mass, that is represented by m bar, and it is defined as molar mass is nothing but the mass of any substance per amount of substance. This is the mass of any substance, and n is the amount of substance. And amount of substance, we know that it has the unit of mole. So the unit of molar mass is basically, we can say that kilogram per mole, or sometimes the molar mass is also measured in kilogram per kilomole. So if we introduce the concept of molar mass in the equation, so molar mass is equal to mass per amount of substance. So sample m will be equal to n m bar. So replacing m with n m bar, we get this expression. Further, if we rearrange this, so we get m bar r is equal to PV by NT. So this m bar r is basically the universal gas constant, or it is also called the ideal gas constant. So r bar will be equal to PV by NT. There is slight difference between r and r bar. R is the specific gas constant, or it is also called particular gas constant, and it has the unit of, if we check from here we can predict the unit of R, which will be PV by T. So P has the unit of Pascal. Pascal is nothing but Newton per square meter, and V is volume, and this V is specific volume. So cubic meter per kilogram divided by Kelvin. So the unit of R will be Newton. This square meter will cancel, only 1 m will remain there. So Newton meter per kilogram per Kelvin. So the unit of R is Newton meter per kilogram per Kelvin, and the unit of R bar is slightly different from this. The unit of R bar can be derived from m bar R. So m bar has the unit of kilogram per kilomole, and the unit of R is already, we derived it, Newton meter per kilogram per Kelvin. So this kilogram will cancel, we will get Newton meter per kilomole per Kelvin. So this is the unit of R bar. R bar is also called molar gas constant, or it is also called universal gas constant. Its value is fixed for all types of gases, while the value of sample R, which is particular gas constant, varies for each and every type of gas. So suppose if somebody asks us to find the particular gas constant for a specific gas, so we can do this. The value of R bar, which is the universal gas constant, has the value 8314.5 Newton meter per kilomole per Kelvin. So we know about the universal gas constant value or molar gas constant value. For example, we have a gas which is oxygen. The molar mass of the oxygen is 32 kilogram per kilomole. So how can we find the value of R, which is the particular gas constant for this oxygen? So how can we find it? We can find it from this very simple expression: R is equal to R bar by M bar. R bar is 8314.5 and M bar is 32 kilogram per kilomole. So if we simplify this, the value of R is 259.83 Newton meter per kilogram per Kelvin. So this value R is only for oxygen. This is the particular gas constant for oxygen. Here is an example in which the ideal gas equation has been used and it is applied. In this example, we have to determine the mass of the air in a room whose dimensions are 4 by 5 by 6 meter at 100 kilopascal and 25 degrees centigrade. So first of all, we will find the volume of this room. So it can be found by length multiplied by height multiplied by width. We get 120 cubic meter. Further, we will need the value of R, which is the specific gas constant. Here air is the gas. So for air we have the value of R, which is 287 joule per kilogram per Kelvin. Also in kilojoule per kilogram per Kelvin, this is 0.287 kilojoule per kilogram per Kelvin. We can convert it to any convenient unit. So the value of R is 0.287 joule per kilogram per Kelvin. Further, we have given the pressure, which is 100 kilopascal, and temperature 25 degrees C. So we will convert temperature into Kelvin, 298 Kelvin. So using the equation PV is equal to mRT, which is the characteristic equation of state for perfect gas. So we are required to find the value of M. It will become PV by RT. P is 100 kilopascal, V is 120, R is 0.287 kilopascal into cubic meter per kilogram per Kelvin. The simplified form of this unit is kilojoule per kilogram per Kelvin, and the value of T is 298 Kelvin. So simplifying this, we get 140.3 kilogram. So 140.3 kilogram air can be accommodated in this room at these conditions, having 120 cubic meter volume at pressure 100 kilopascal and temperature 25 degrees C. Here is another example. In this example, again the application of ideal gas equation has been used. So the statement of the example is: a vessel of volume 0.2 cubic meter contains nitrogen at 1.013 bar and 15 degrees C. If 0.2 kilogram of nitrogen is now pumped into the vessel, calculate the new pressure when the vessel has returned to its initial temperature. The molar mass of nitrogen is 28 kilogram per kilomole, and it may be assumed to be a perfect gas. So in this problem we have given the volume, which is 0.2 cubic meter, and pressure P1 at initial stage is 1.013 bar, and temperature T1 is 15 degrees centigrade. Further, mass 0.2 additionally was added. So this is the additional mass added. After adding this amount of mass, we have to find the new pressure, which is P2, and the final temperature T2 is equal to the initial temperature. Also the molar mass of gas is 28 kilogram per kilomole, and it will be assumed that it is a perfect gas. Nitrogen is a perfect gas. So we will first take the initial state before pumping 0.2 kilogram of nitrogen. We will use this equation for state 1, and after pumping, when we pump 0.2 kilogram of nitrogen to the vessel, after that we will use this equation. This is for state 2. So we are only required to find the new pressure in this problem. So first of all, we will find the mass, initial mass, which was present in the nitrogen. For that we will need the value of R. So R can be calculated very easily because we know the value of R bar and M bar. So from this we can find the specific gas constant or particular gas constant of nitrogen, which is 296.95 Newton meter per kilogram per Kelvin. Also the value of T1 is given, P1 is given, and V1 is given. So putting these values in this equation and rearranging it for M1, so M1 can be calculated from here, which is 0.237 kilogram, and further when we pump 0.2 kilogram of mass, so now we will add both of them, 0.237 and 0.2. So when we add 0.237 kilogram and 0.2 kilogram, we get 0.4837 kilogram. This is the mass after adding 0.2 kilogram. Now at this amount of mass and the other conditions are given, specified, we will find the new pressure, which is P2. So rearranging this equation for P2, we know M2, which is 0.437 kilogram. R is given, T2 is same as T1, V2 is same as V1 because the vessel is rigid and there is no change in volume of the vessel, so V1 is equal to V2. After pumping and before pumping, the volume of the vessel remains constant. So at these conditions, P2 comes out 1.87 bar. Further, another example for the application of ideal gas equation. So the statement of the example is: a certain perfect gas of mass 0.01 kilogram occupies a volume of 0.003 cubic meter at a pressure of 7 bar and a temperature of 131 degrees centigrade. The gas is allowed to expand until the pressure is 1 bar and the final volume is 0.02 cubic meter. We have to calculate two things: molar mass of the gas and the final temperature. Again we have two states, before expansion and after expansion. So mass is given, which is 0.01 kilogram. Volume initially V1 is given, which is 0.003 cubic meter. Pressure P1 is given, which is 7 bar. Temperature T1 is given, which is 131 degrees centigrade. After expansion, the pressure is given, which is 1 bar, and volume after expansion is given, which is 0.02 cubic meter. So at these conditions, first of all we will find the value of R from this. So using the equation for state 1, P1 V1 is equal to MR T1. So R can be found for this, which is 520 Newton meter per kilogram per Kelvin. Now we can find very easily the molar mass of the gas, because we have the expression R is equal to R bar by M bar. So from here R bar is known to us, which is 8314.5 Newton meter per kilomole per Kelvin, and the value of R is calculated here, 520 Newton meter per kilogram per Kelvin. So the value of molar mass of the gas is 16 kilogram per kilomole. Now finding the final temperature, which is T2, for that again using this equation P2 V2 is equal to mR T2, we have these values P2 V2, similarly R and M we are given 520, it is calculated here. So the final temperature using this equation we get 111.5 degree centigrade. Further discussion is about the properties of perfect gas. This term is very important, specific heat capacity. So how can we define it? This is the amount of heat required to raise the temperature of a unit mass substance by 1 degree. So represented by C, amount of heat required to raise unit mass of substance by 1 degree. So this is the mathematical expression for specific heat capacity. There are two types of specific heat capacities which are very commonly used. One is specific heat capacity at constant pressure, and second is specific heat capacity at constant volume. The unit of specific heat capacity is same for both types, and that is joule per kilogram per Kelvin, or kilojoule per kilogram per Kelvin. This relationship is sometimes used in solution of the problem Cp, Cv and R. So this is basically the derivation of the relationship, that how can we derive the relationship between Cp, Cv and R using non-flow equation. So it is already assumed that we have perfect gas, and the non-flow equation for this is Q plus W is equal to U2 minus U1. Further, the difference of internal energy is equal to mCv T2 minus T1. So it can be written like this. We know that for constant pressure process, W is calculated from this expression, which is minus mR into T2 minus T1. So if we substitute the value of W, the expression of W in this equation, we get this. So rearranging it, we will get this expression. Further, for constant pressure process, we know that Q is equal to mCp T2 minus T1. So the value, if we put the value of Q here, so finally we will get this expression. So T2 minus T1 is common in both sides, so it will cancel, and finally we will get Cv plus R is equal to Cp. M is also same on both sides. So this relationship is achieved, which is Cp minus Cv is equal to R. So if we know about the value of Cp and Cv for a gas, then we can easily find the value of R as well from these specific heat capacities at constant pressure and constant volume. Specific enthalpy of a perfect gas. So we know that the enthalpy, specific enthalpy is equal to specific internal energy plus product of pressure and specific volume. Further, we know that PV is equal to RT, and the value of internal energy is from Joule's law, that is U is equal to Cv into T. So if we put U, replace U by Cv into T plus PV by RT, so we get H is equal to CVT plus RT. T is common in both, so it will be written like this, Cv plus R into T. Further, we have relationship Cp minus Cv is equal to R. So if we rearrange it and we write it like this, Cv plus R is equal to Cp. So then this Cp can be used to replace this. So H will become equal to Cp into T. Further, for mass M, we can also write that the enthalpy of the perfect gas is capital H is equal to mCpT. Small h is for specific enthalpy, where H is for only enthalpy. This has unit kilojoule per kilogram per Kelvin. This is the unit of the specific enthalpy, and it has the unit of kilojoule per Kelvin only. Similarly, another term is the ratio of specific heat capacities in the study of perfect gas. It is also an important terminology represented by gamma, also called adiabatic index. This is the ratio of specific heat capacity at constant pressure and specific heat capacity at constant volume. So as we know that for perfect gas, the value of Cp is always greater than Cv. So the value of gamma is always greater than 1 for all types of perfect gases. For monoatomic, diatomic and triatomic gases, gamma value varies. For monoatomic gases, it has the highest value and it is taken as 1.6. For diatomic gases, its value a little bit decreases and it is taken as 1.4. For triatomic gases, the value of gamma is 1.3, and as long as the value, the number of atoms increases in a perfect gas, the value of gamma decreases. For example, for ethane it has the value 1.22, while for isobutane the value of gamma is 1.11 only. So from gamma we can predict that how much atoms are there in the perfect gas. If the value of gamma is greater, so we can say that it has monoatomic or diatomic structure, and if it has less value, so we can say comparatively it has many atoms in the gases. Other important relationships which are very important can be achieved further from the already expressions available. That is, if we divide this expression by Cv, so Cv by Cv is basically gamma minus 1 and R by Cv. So Cv is equal to R by gamma minus 1. We can write it like this. Further, from the definition of gamma, which is Cp is equal to gamma into Cv, if we put the value of Cv here in this expression, so we get Cp is equal to gamma R by gamma minus 1. These are very simple expressions but are very much important to use in the problem solution of the perfect gases. Here is an example, example 2.10. In this example, certain perfect gas has specific heat capacities Cp value which is 0.846 kilojoule per kilogram per Kelvin, and Cv is 0.657 kilojoule per kilogram per Kelvin. we have to calculate the gas constant and the molar mass of the gas. So in this example we have to find the value of gas constant R and the molar mass of the gas. So we have given Cp and Cv. From the difference of these both we can get the value of R. So R comes out 189 Newton meter per kilogram per Kelvin. Similarly, to find the value of molar mass, we have the relationship molar gas constant divided by molar mass of the gas. So if we rearrange it for molar mass, R value is known to us, which is 8314.5, and the value of R is 189 Newton meter per kilogram per Kelvin. So from this we can easily find the value of molar mass, and it comes out 44 kilogram per kilomole. This is all about the properties of perfect gas. Next we will discuss lecture number 7 on another topic. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.